Right, so this is a video on acids, bases and pH. It's going to concentrate mostly on acids really and pH, with bases and Kw, the dissociation, the ionic dissociation of water, the constant, coming up in a separate one. So I'm going to concentrate really on acids and pH, but I will mention bases at the start. As is my new little thing, I'm going to, any of these notes, I'm going to put this in the little description, and if you want to download this and use this as notes, you're more than welcome to. A few people have asked in the past, so yeah. Okay, acids and bases definition. So I'm not going to bother with Lewis acids and bases, because that's sort of better fitted to a different topic really. That's better later in unit 5 as it would be right now as I'm doing this, but in the future it'll be in a different unit as we go into the year 2 of the AQA stuff. All very confusing, but it fits better in some of the complex ion stuff, the transition metal things. So the definitions I'm looking at is the Bronsted-Lowry definition, and so Bronsted. It's a bit fine, that pen, really, isn't it? Let's unfine it. There we go. So the Bronsted-Lowry definitions of acids and bases are that an acid is a proton donor. It's hopefully going to be quite a quick video, really. That's my new thing, short videos. And a base is, in sort of simple terms, a proton acceptor. And you get various questions where they basically give you a situation. They'll ask you, what's the acid, what's the base, and all the rest. One could be, let's have a think. I'm trying to think of one that I can think of here. You could an equation for each one to show the idea of the of an acid and a base. I guess we could have something like NH3 H plus becoming NH4 plus. We can see that in the process of going as the reaction takes place, the ammonia gains the H plus ion, therefore becoming the ammonium ion. So that's acting as a base, clearly acting as a base. An acid, we could have something like I guess we could do a reaction like this, which would probably pinpoint some of it. Just check that's balanced. Yep. So in this case here, what we've got is the idea of the hydrochloric acid donating its proton to the water, therefore acting as an acid, the proton donor. The water, on the other hand, here has accepted a proton. Water can act as an acid or a base, it depends on the situation, but it's accepted the proton, becoming this hydroxonium ion here, the H3O plus, therefore acting as a base. So acid, base in this case. These kind of questions do come up, but they're less common, and they're quite straightforward really, provided you know this definition of proton donor and proton acceptor for acids and base respectively. You shouldn't have any real issue kind of working out what's going where. Just look at literally where the protons or the hydrogens really have gone to. They've left this one, therefore this has to be acid. They've gone to this one, therefore this must be the base, and obviously another one there, a little bit there. I'm not going to touch on bases anymore there. They're going to come up in a different video. I'm going to concentrate on this point on acids and pH. And this term pH is quite a nice one. pH is something that people, I guess you look at particularly in school and things from probably about year 7. You look at what the term pH means, I should say. And so people are normally quite comfortable, I guess, with the idea of pH as having acids having low pHs, bases or alkalis having high pHs, and neutral being around this sort of middle area of 7. And those are the numbers we tend to associate with pH as well. Normally we would go from 1 to 14 is sort of the junior school, or lower down junior end of senior school, the numbers associated. But the numbers really can be much sort of less and greater than that. We can have negative pHs, and really the scale that's better to use, I suppose, and it's still very simplistic, would be a scale of 0 to 14, just to highlight something that I'm going to look at in a second. So this scale, as I say, can go into the minus figures, and it can go greater than 14. It just tends to be a sort of a nice scale that we can use where we can put things on here and we can say that this is the strong acid, this is the strong base or strong alkali, neutrals in the middle and all the rest. And all pH is, it's a simplified scale, it's a logarithmic scale. It takes a very, very wide range of numbers. The numbers are, if we're dealing with something that has a pH of 0, pH, by the way, is just a relation to the concentration of hydrogen ions. And I'll define this properly in a second. So if we said that a solution has a hydrogen ion concentration of 1 mole per decimeter cubed, we would say it has a pH of 0. If on this hand, though, it has a pH of 14, that means it has a concentration of 1 times 10 to the minus 14 mole per decimeters cubed. And we can see there's a vast range of numbers there. There's a huge difference between 1 and 1 times 10 to the minus 14, whereas actually when we look at the pH scale, 0 to 14, very manageable, very easy to deal with. So the pH scale is very, very useful, and we can convert these numbers into pHs, and we can convert the pHs into the actual concentrations. Because it's a log scale, pH basically, pH is equal to the minus log of the hydrogen ion concentration. So square brackets equals concentration in moles per decimeter cubed. So minus log of the hydrogen ion concentration. It's literally a case, if you've got a hydrogen ion concentration, you put it in here, you minus log it, and you get an answer for the pH. So if you put 1 into here right now and you do minus log of 1, you will get 0. If you do minus log of 1 times 10 to the minus 14, you will get 14. It's as easy as that. Very, very straightforward. This is a definition of pH. Okay, that there is a definition of pH. You don't need to worry about it doing it in word format. You are more than welcome just to do it as pH equals minus log of the hydrogen ion concentration. Square brackets and all the rest, you've got to have that there. Because if it's normal brackets, it's not denoting the concentration of. But if you write that in an exam, you're going to get 1 mark. That's quite nice. You can flip this around slightly, and those of you who are mathsy, unlike me, you can work out the hydrogen ion concentration from the pH, and that is apparently as simple as saying 10 to the power of minus pH. And again, you could put these numbers in, and you could do 10 to the power of 0, basically minus 0, and you would come out with 1 there as your answer. Nice. And again, 1 times 10 to the minus 14, and all the various bits in between. Bear in mind, we don't have to have 1 times 10 to the minus 14. We could have 1.67 times 10 to the minus 14, you know, and all these other horrible numbers in between. So how would you, in an exam, what you're going to come across? I'm not going to do any exam questions on this one because they tend to come into the grand scheme of things with more of the acids and bases. This is more of a kind of a really introductory one, hopefully quite quick, although I do tend to go on. So what you might get in an exam, I'm going to give you 3 sort of questions. I'll write it out first, and you can then check if you've got it right. If you want to go ahead, you can do. So you could be asked to find the pH of the following: 0.15 mole per decimeter cubed, and I'll run through each one in turn. So what's the pH of that? Now, either you've paused that and then are now waiting for me to work it out, or you're just waiting for me. Either way, it doesn't matter. The way I tend to do this is I first of all look at the dissociation here that's occurring. So we've got strong acids, okay, and we'll look at weak acids as a separate video, but strong acids dissociate in this way. And it's a bit of a simplified format, but it kind of works. It's very similar to this bit up here with my hydroxonium ion, but it's a nice simplified version where I've not included water. I think it just makes it a little bit more straightforward. So key thing is my hydrochloric acid, my hydrogen chloride molecule dissociates in water to give me 1 H plus ion and 1 chloride ion. And that's very important because the dissociation is 1 to 1, which means the concentration therefore of hydrogen ions is 0.15. So pH is minus log of 0.15. Now I don't have to use square brackets because I'm putting an actual value in. Minus log 0.5, it's going to be 0.82. Now, important point to note here, I'm not going to change colour, 2 decimal places always. Always give your answers for pH to 2 decimal places. They'll normally specify in a question, always 2 decimal places. Obviously rounded correctly whatever this was, I can't remember exactly what this was now, 0.821 for example, rounded to 0.82. If it was 0.825, 0.83 would be my answer. So round correctly and do it to 2 decimal places, please. We could have another one, and this is a good example for a reason that I almost gave away then, but I don't want to ruin it. Do make sure you stick the minus in as well. Don't get messed up with that one. Okay, do put that in. Nitric acid, 2.64 mole per decimeter cubed. Nitric acid, pause and do it. I don't know, or you just listen to me, whatever. Again, dissociation, HNO3 to H plus and NO3 minus. So same thing before, it's 1 to 1. Giveaway here is the fact that we've got the H there, only one H, splitting, boom, right down there. Same thing, concentration was 2.64, means this is going to have a concentration of 2.64 as well. So we go pH is minus log of 2.64, and we get an answer of, this time, minus 0.42. So bear in mind, it's just a logarithmic scale. It doesn't mean there's actually negative ions. There's not. There's obviously a very high number of ions, actually, but the fact that it's logarithmic makes it a minus. Again, 2 decimal places, very, very important. And finally, last but not least, and this will be the end of the video after this one, on 0.315 mole per decimeter cube. Solution of sulfuric acid. Pause and do things. Okay. Slight trick here, and I like to use these examples again with the bases as well, which I'll look at in a different video. They like, tickling my throat. They like to use in this case what we call a diprotic acid for good reason, and that's because when we have H2SO4 we find that it dissociates into 2H plus and an SO4 2 minus. Therefore my concentration of H plus in this case is 0.315. Looking at the ratio 1 to 2, 0.315 times 2, therefore 0.630. But then the calculation is the same. It's the minus log of 0.630, and that gives us a value of 0.20. What lovely numbers these are. 3 calculations there. Looking at calculating the pH, bit of definition of the acid, term acid and term base, bit of linking it to some equations, not a huge amount there because you could go on all day looking at various equations, but really it's about practicing and making sure you're happy with where the acid and the base is, but it's all to do with these definitions. Obviously dissociation here I think is a key one because it really helps you work out what your concentration is going to be, particularly here where we've got a double. Besides that, that's basically your bases, a little bit of bases, acids, and your pH calculations, which then span into all these other topics of acids and bases. Any problems? Comment. Remember, you can download these notes if you wish. Otherwise, good luck with those.